For this problem, we are supposed to graph this function. This is a little different looking function than we usually have. We do have the f of x equals, but then there's three different parts to this. This is called a piecewise defined function. This graph is going to have three different pieces that we are going to have to graph. There's a couple of different ways of approaching this problem. One of them would be using a table, and then the other is using our parent function knowledge and our knowledge of transformations to be able to go through and do these problems. To start with, we do have f of x equals, and then there's this big bracket, but all they are really telling us is that we have three separate equations, and what we could do for each one of these is we could simply put a y equals or an f of x equals in front of each one. So I'm going to just write those in like this, just to kind of make this a little more separate so that it looks like three separate equations. It's technically just one big equation, but how we're going to approach this, we're going to graph this absolute value graph for just a certain portion of the graph. Do the same thing with the green, the same thing with the red. Let's start with that blue graph. That blue graph is y is equal to the absolute value of x plus 2. I'm going to cut this graph up into kind of two pieces. So first, let me just talk about y is equal to the absolute value of x plus 2. If you're going to do this graph the fast way, what you need to remember is what the parent function looks like for absolute value. Our absolute value parent function is a V-shaped graph. And as a quick reminder, it looks like that. So the vertex is at 0, 0, and then the left and the right sides, those are straight to give us that V-shaped graph. So this is going to be a V-shaped graph. That's what the parent function tells us, and its vertex is at 0, 0. But we do have, in this problem, a transformation. We have in the parentheses, or in the absolute value rather, an x plus 2. Anytime you have addition or subtraction, when you compare a function to its parent function, that's going to have some shift. It's going to slide the graph either up or down or left or right. This is in our grouping symbols of absolute value, so that's horizontal. And if you have addition, that is going to slide our graph over to the left. So this blue equation, if we do this the fast way, instead of making a table, would be to recognize that our graph for the parent function looks exactly like this, but we do need to go to the left 2 units. So if you were to graph y is equal to the absolute value of x plus 2, it would look like this. Parent function has its vertex at 0, 0. The transformation tells me I need to slide that over to the left 2, so this is the vertex, the bottom part of the V, and then the two branches that are there, they can vary in steepness, but this one is going to be the same as the parent function, which has a slope of 1 and negative 1 on each side. So it's going to look basically like this. So that is what this graph looks like. Y is equal to the absolute value of x plus 2 looks exactly like this. But we don't want the entire graph. We only want values of x that are less than 0. So what does that do to our graph? Well, that means that we need to cut part of this graph off. Our inequality is x is less than 0. Let's talk about what x equals 0 looks like. X equals 0, that is a vertical line when x is equal to 0. So here's where x is equal to 5. Here's where x is equal to 7. Here's where x is equal to a negative 6. X equals 0 would be a vertical line right on top of the y-axis. So we're going to have to cut our graph right there, and we're only going to keep one side of that, either the left or the right side. And if we look at this, Inequality, we only want to keep the values of x that are smaller than 0. So I'm going to put in a dotted line right here. It's not really part of the graph, but it's going to tell me where to cut. And I need to keep one side or the other. And my inequality says we only want the things that are smaller than 0, which would be the left side of this graph. So the right side is actually going to get cut off, and it's not going to be part of our final answer. One last thing, when your graph hits a cut line, you have to either put an open or a closed circle there. And you can just look at your inequality to figure that out. This is x is less than 0. If it's less than or greater than, that should be an open circle. So when it hits the black dotted line, our graph should have an open circle at that point. Okay, so that is the first part of our graph. The second part of our graph, we're going to be looking at the line y equals x minus 2. That is a line. It is in slope-intercept form. So b, our y-intercept, is at -2, and our slope, m, is equal to 1. So if you were going to go through and do the entire graph of y is equal to x minus 2, we would graph our y-intercept first at -2, and then we would have a slope of 1, which would be up 1 over 1, up 1 over 1, up 1 over 1, and so on. And our line, if we graph the entire line forever and ever in both directions, the graph of the equation y equals x minus 2 would look like that. But for this problem, we don't want the entire line. We only want the line in between 0 and 2. So I'm going to put in, again, just like here we had x and 0, so I put in a vertical line at 0. Here I have 0 and 2, so I'm going to put in a vertical line, 2 cut lines, one of them at 0, and one of them at 2. And then I need to only keep the parts that we want. And this inequality says we only want the values in between 0 and 2. So for my final graph, I don't want this section over on the right. Those x points are all bigger than 2. I don't want this section on the left. Those x values all have an x coordinate of less than 0. I only want the stuff in between 0 and 2. And then wherever our line touches one of these cut lines, we need either an open or a closed circle. And these two inequalities are both less than or equal to. For less than or equal to or greater than or equal to, we want a closed circle. So for this green equation, this is what we want for our graph. So here was our first graph with the absolute value. Now I need to take this and put that on our graph right here. So from my point here up to my point right here, I draw that in, and we do have another cut line right here which we could draw in as a reference. These cut lines you do not have to draw in. They're not part of the final answer. You won't see them in the back of the book when you take a look at your odd answers. So we just graphed the line y is equal to x minus 2, but we only kept the part of the line that was from an x coordinate of 0 over to an x coordinate of 2. We have one more equation that we need to go through and graph, and that is the red equation. For our red equation, we have y is equal to the square root of x minus 2. If I use the parent function idea to approach this problem, I need to remember what the square root graph looks like as a parent function. It looks like that. There's an important point at 0, 0, and then it has this general shape. Inside the square root, we have an x minus 2, Anytime you have addition or subtraction, that'll slide the graph either up or down or left or right. If it's inside your symbols, inside your grouping symbol, and the square root is kind of a grouping symbol. It's not exactly the same as parentheses because we have to do other things, but it's a grouping symbol, kind of like absolute value is a grouping symbol. So I want the equation, I want the graph to be from the equation y equals the square root of x, but then I need to subtract 2. That is inside grouping symbols, and addition inside grouping symbols will slide the graph over to the right. So we are going to take the square root graph, this one right here, important point at 0, 0 with this shape, and we're going to slide everything over to the right 2 units. So here's our graph. I know that the parent function starts here with an important point at 0, 0, but we need to move it over to the right 2 units, and then you need to have a square root shape which looks something kind of like that. When I look at our inequality, we have x is greater than 2. So just like we did for the other 2 graphs, I'm going to put in a vertical line at 2 for this problem. The first one only had a vertical line at 0. The second one had a vertical line at both 0 and 2 because they were both listed there with the inequality. This red one, we only need a vertical line at 2. So I'm going to put in a vertical cut line at 2. And then I'm only going to keep one side of that graph. I only want the stuff for x that is bigger than 2. And that is this right side. So I would erase everything over on the left side, except this graph didn't have anything on the left side anyways. And then where our graph hits our cut line, I need to decide if it's an open or a closed circle. In this problem, we have greater than, and greater than is an open circle. So here at the cut line, I need to change that point to an open circle. So this is what the graph of y is equal to the square root of x is less than 2 looks like when you only include values of x that are greater than 2. It's an open circle here at the point to 0 and then over to the right. And I need to take this piece and I need to put that on our final graph. So here are the first 2 pieces. Now I need to put in a square root graph over on this right side. I need an open circle here at 2, 0, and then I need the square root shape so it would look something like that. This is a reasonable sketch for your final answer. We have taken 3 separate graphs. We usually would have a square root graph that would go on forever in both directions. We have a line that would usually go on forever in both directions. And we have our square root graph, but we've cut them up into 3 sections and only included the parts from each section based on these inequalities. It typically is faster to use a parent function approach with your transformations to go through and do this problem than it is for you to make a table. But the problem can be done either way. This is what our final answer could look like. If you want to keep those cut lines in there, you can. Otherwise, again, what you would see in the back of the book for a solution would be this graph without the cut lines in there. It's fine either way. You can get full credit either way on those. And the only other thing that I wanted to point out is here, where we have an open and a closed circle together, that basically just ends up being a closed circle. The closed circle fills in the open circle, and you end up with just a closed circle at that value.